Hello everyone, hope you are all doing fine. I'm starting a new lecture series on equivalent resistance, and this will be our first lecture on it. In this video, we're going to learn about what is equivalent resistance, and we'll also derive the formulas for the equivalent resistance for the cases of series and parallel combination of resistors. So yes, my name is Vijay Krishna and you're watching UpPhys channel. Let's get started. First, let us understand the definition of equivalent resistance. Okay, so the definition of equivalent resistance is given over here. Just pause it and read it. Read the statement. But anyhow, I'm going to explain it in a simplest way. Okay, if a circuit has many number of resistors in it, and which are connected something like this, many number of resistors as you can take. Okay, if I replace all these resistors, if I replace all these resistors with a single resistance, with a single resistance, that resistance is called equivalent resistance. Okay, in a simplest way, if I can replace the entire circuit of resistors, branches of resistors, into a single resistor, then that single resistor, resistance of that single resistor is called equivalent resistance. Okay, right. Now let us derive the equations for the formulas for the equivalent resistance for the case of resistors connected in series. Okay, let us take two or three resistors. Okay, now this is resistor R1, sorry, resistor R1. This is resistor R2 and this one is resistor R3. Now these resistors are connected to a battery of potential difference V, let it be. Okay, now as these are connected in series, end-to-end connection, then the current through each resistor is same. In case of series combination of any kind of electrical element like resistors, capacitors, or inductors, whatever the electric component is, when they are connected in series, the same current flows through every component of the electric circuit which are connected in series. So current will be same through every resistors, all the three resistors. Okay, now if I apply the Kirchhoff law, I'm taking Kirchhoff second law, especially Kirchhoff second law. I'm taking the loop in the clockwise direction. I'm starting from the battery, I mean the power source, the energy source. This is negative, positive, lower potential to higher potential. This will be V, and here we have the potential. Here it is positive and negative because the current always flows from higher potential to lower potential. This is higher potential and lower potential, and there is potential drop in the direction of loop. So I'm taking it as negative I R1, and the other case is for this also I R2. For this one it is I R3 is equal to 0. Okay, now V minus I, if I take I common, R1 plus R2 plus R3 is equal to 0. Now I is equal to V by R1 plus R2 plus R3. Okay, now if I replace this entire combination of resistors with a with an equivalent resistance R equivalent, then also the current would be same, and we have applied the same voltage source. Now the current equation would be V upon R equivalent. V upon R equivalent. If I compare these two equations, I'll be getting R equivalent for the series combination of resistors, which is R1, R2, R3. If the circuit has many number of resistors which are connected in series, then it will be like R equivalent is equal to R1 plus R2 plus R3, so on, till n number of resistors. Okay, let us say let us say if n number of resistors of equal resistance of all the resistors are same. Okay, how many number of resistors that I have connected? N resistors. N resistors. If I would have connected n resistors in series, all the resistance of all the resistors is same, then the equivalent resistance will be R plus R plus R n times. That means n into R. Okay, n into R. So this is the equivalent resistance formula when the resistors are connected in series. Resistors are connected in series. Okay, in case of series combination, current remains same. Current remains same through all the resistors. Through all the resistors. Hope this, derivation for the equivalent resistance of the resistors which are connected in series, right? Okay, now let us move on to the next step. Let us derive the equation for the equivalent resistance when the resistors connected in parallel. Keep it in mind that when the resistors or any electrical components connected in parallel, then the potential difference across every branch will be same, which are in parallel, of course, which are in parallel. I'm taking three resistors again. 1, 2, and I've taken three resistors. Now, let this be R1, R2, R3. Now, these three resistors are connected to a voltage source of potential difference V. Now, as you can see, the potential difference across these two ends, let's say this is 0 and this is V. If this is 0, this will also be 0, and this will be 0, this will be 0, this will be 0. If this is V, this will also be V, this will be V, this will be V. So potential difference across all the resistors is same. Okay, I'm going to draw it again. Let me take out all those. Okay, so as these resistors are connected in parallel, the potential difference across all the resistors is same. Here the potential difference is V. Here also the potential difference is V again, and here again the potential difference is V. Now let's say the current flowing through the entire circuit is I. This current is divided into three parts here. Here it is I1, here it is I2, here it is I3. Now as I already know from Kirchhoff's laws, total current I flowing towards the junction is equal to current flowing away from the junction, right? Right? Okay. Now total current I is equal to V by R according to Ohm's law. So V is total potential V by R. I am writing it as R equivalent. R equivalent because this entire combination of resistors can be replaced with a single resistance of single resistor of resistance R equivalent. So V by R equivalent is equal to, here the potential difference is V again by R1, here it is R1, and again V upon R2, V upon R3, because across every resistor the potential difference is same. I've taken the same potential difference, and the resistance of the resistors R1 and R2, R3, current I1 is V by R1, current I2 is V by R2, current I3 is V by R3. If I take this V common, this V will get cancelled out, and I am getting the final result as 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Right? Now, as I need the formula for the equivalent resistance. So R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 whole inverse. This is the required formula for the equivalent resistance when the resistors connected in parallel. If this circuit has n number of resistors which are connected in parallel, Then the equation will be like R equivalent 1 by R1 plus 1 by R2 plus 1 by R3 so on 1 by Rn whole inverse. As I've already discussed in the earlier case, if I would have taken resistors of resistances of equal resistances, okay, then if R1 is equal to R2 is equal to R3 is equal to so on, Rn is equal to R. That means resistances of all the resistances are all the resistors is same, and I have taken n resistors. In such a case, R equivalent will be 1 by R plus 1 by R plus so on n times whole inverse, whole inverse, right? Whole inverse. Now, as it has n times, so n by R whole inverse, which is R by n. So final result, when I have connected n number of resistors of equal resistances, then the equivalent resistance R equivalent is equal to R upon n. In case of series combination, we have obtained the equation for the equivalent resistance when the resistances of the resistors connected in series are same, that is n into R. In case of parallel, it is R by n. Let's just say, to remember the direct formula, if two resistors of resistances R1 and R2 connected in parallel, then R equivalent is equal to 1 by R1 plus 1 by R2 whole inverse. Okay, this can be further simplified if I take LCM R1 R2 R2 plus R1 whole inverse. Now the final result will be like R1 R2 by R1 plus R2. Whenever we come across a situation like two different resistors which are connected in parallel, then we can directly use this formula R1 R2 by R1 plus R2. Okay, right. This is all about series and parallel combination of resistors. In the next lecture, we are going to discuss how to find the equivalent resistance, okay, by using different methods, most probably reducing method. Okay, right. So that's it in this video. If you like the video is helpful, please do like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. So thank you very much for watching. See you in the next video.